Hello and welcome back to the deep dive. Today we are opening a fresh page in our preparations. We're starting with Unit 1, Solutions.
A very important unit.
Very important. And specifically, we're going to focus on the very first foundational topic, types of solutions. We've gone through the standard textbooks, the insert notes, all the concept guides to extract exactly what you need.
That is correct. And the mission for this deep dive is very specific. We want to move beyond just memorizing a definition.
Right.
We want to understand the physics of what is happening,
Yeah.
inside the beaker. We want to visualize the particles, because if you understand the what and the why, the definitions will stick in your memory automatically.
I like that approach. So let us start with a question. A very simple, everyday scenario that everyone listening has experienced.
Okay.
You are making a cup of hot tea in the morning. You take the hot water, you add a spoonful of sugar, and you give it a stir.
A standard morning ritual, yes.
Indeed. But look closely at what happens. You see the white crystals drop in, you stir, and then, poof, the crystals disappear. The liquid becomes completely clear again. Now imagine you pour that tea into two different cups, one for you, one for a guest. Does one cup taste sweeter than the other?
No. I mean, provided you have stirred it properly, both cups will taste exactly the same amount of sweet.
So here's the mystery we are solving today. Where did the sugar go? And perhaps more importantly, why doesn't it just sink to the bottom if you leave that cup sitting on the table for an hour?
It's a very valid question.
Yeah.
Gravity is pulling on the sugar, yet it just stays up.
Precisely. That is the mystery of the solution. So let us deep dive into this. Why do we care about this topic? Is it just for marks in the board exam?
Well, the marks are important, of course, no doubt. But conceptually, this topic is the foundation for the entire unit. Understanding types of solutions explains why a mixture has uniform properties everywhere.
Uniform properties.
Yes. It explains why a drop of tea from the top has the same density, the same sweetness, the same concentration as a drop from the bottom.
It's about consistency then.
It is about reliability. And for the board exam, this is how the examiners can trick you. They test if you can distinguish a real solution from other mixtures that might look similar.
But behave differently.
Exactly. If you miss this basic concept, the numerical questions later in the chapter, they just won't make sense.
Okay, let us break this down. For a student sitting in class 12 who is perhaps struggling with the chemistry jargon, give us the zero-level explanation. No complex formulas yet. What exactly is a solution?
At its absolute simplest, a solution is a homogeneous mixture. You have one substance, which we call the solute, and it dissolves, and this is the word, completely in another substance, the solvent.
Now, homogeneous is one of those heavy academic words. Let us unpack that for a moment.
Homogeneous simply means it has the same composition throughout. It forms a single phase. To your naked eye, it looks like just one distinct material.
So you don't see sugar and water separately anymore?
No. You just see sweet water. It looks uniform.
The notes here have a very interesting section on visualization. I think this is where many students get stuck. They can't really see the particles. Let us try to picture this mentally.
This is very helpful. I want everyone listening to close their eyes for a moment.
Okay, I'm imagining a glass beaker filled with water.
Now zoom in. Imagine you can see the water molecules. They're not sitting still. This is important. They are vibrating, rotating, dancing around each other. It's a chaotic crowd of molecules.
So it's a very busy place. Now, I'm dropping in a crystal of salt.
Right. That salt crystal is a solid block. The ions are holding onto each other very tightly. But the moment it hits the water molecules attack.
Attack. That sounds a bit aggressive.
It is an energetic process. The water molecules, you see, they surround the salt ions on the surface of the crystal. They use their own electrical charges to pry the ions loose.
So they're literally pulling them away.
They separate them from their neighbors and essentially pull them into the crowd of water.
So the crystal structure is actually being taken apart.
Completely destroyed. The ions are now floating alone, completely surrounded by water molecules. They have been separated.
And what is this process called officially?
This is called solvation. The solvent molecules use their polarity to surround the solute particles. They effectively kidnap the solute particles one by one and hide them in the crowd.
Kidnapping the particles. I think that image will stick.
And because everything is moving and colliding randomly, these kidnapped particles get spread out evenly throughout the entire beaker.
So we have the visual. Now, for the students who need to write a precise answer in their exam script, we need the anchor definition, the one that is safe for insert and the board exam.
Yes, you cannot write kidnapping on your answer sheet. The definition you need to memorize is this. A solution is a homogeneous mixture of two or more substances,
Okay.
in which the solute is uniformly distributed at the molecular level in the solvent, forming a single phase.
Let me repeat that key phrase. Uniformly distributed at the molecular level. Why is that specific phrase so critical?
Because that phrase protects you from the biggest misunderstanding students have in this chapter.
And what is that trigger point?
Students often confuse solutions with suspensions.
I see, like muddy water.
Exactly. Think about muddy water. If you stir mud into water, it might look brown and mixed for a moment, but is it a solution?
No, I suppose not.
Why not? Because in a true solution, the particles are separated at the molecular level. You cannot see them, even with a microscope. And most importantly, they do not settle.
Right,
You can leave salt water on a shelf for 50 years. The salt will not sink.
but with muddy water.
In a suspension, the particles are large clumps. You can often see them. And if you let it sit, gravity wins. The mud settles to the bottom.
So the test is time. Solutions are stable. Suspensions, they settle.
Correct. That is the fundamental difference.
Let us try to cement this idea of homogeneity with an analogy. I saw a reference in the source material to the concert crowd. This seems like a fun way to look at it.
I love this analogy. It maps perfectly to the molecular behavior.
So imagine a huge music concert. The stadium floor is packed with people. That crowd is your solvent, the water molecules,
Right, they're all moving, bumping into each other, dancing.
a dynamic, moving liquid made of people. Now imagine a group of 20 friends arrives together. That group is the solute crystal. But they don't stay in a huddle, do they?
No, they want to dance, so they squeeze into the crowd.
And very quickly they get separated.
Lost in the crowd.
Exactly. One friend is near the stage, one is at the back, one is in the middle. Now here is the point. If I were to take a drone photo of that crowd, I wouldn't be able to point to one spot and say, here is the group of friends.
No, they are distributed everywhere.
And this explains the sampling concept we talked about.
Yes. If you took a picture of the front left corner and another picture of the back right corner, statistically, you would find the same ratio of friends to strangers in both photos.
That is homogeneity, uniform distribution.
It is. And it also highlights why you cannot filter a solution. Imagine trying to put up a fence in that crowd that catches only the friends, but lets the strangers pass.
It's impossible.
Impossible because they're too well mixed. In the same way, you cannot filter salt out of water using simple filter paper. The particles are too small and too well distributed.
That brings up a deeper question. Why did chemists actually need to invent this specific label solution? Why not just call everything a mixture and be done with it?
That is a very valid question. It really comes down to solving a problem. Prediction.
Prediction.
We need to know how a substance is going to behave in the future.
Can you give us some historical context on this?
Sure. Go back to the 18th or 19th century. Chemists were mixing random things in beakers. They noticed that some mixtures were, cloudy and unstable. They would separate overnight.
Yep.
But others were clear and stayed that way for years.
So the label solution is essentially a stamp of stability.
Exactly. It's a predictive category. If I label this bottle a solution, I am telling you three things. First, it's transparent. Second, it will not settle. And third, you cannot separate it with simple filtration. It tells a scientist, this is stable.
That makes a lot of sense. It is a classification of behavior, not just composition. Now, let's go back to that visualization. We did the concert crowd, but I want to go strictly microscopic again. Let us run a mental movie.
Let us do it.
Close your eyes again. Picture that glass of salt water. But this time, imagine you have a super powerful microscope one that can see individual atoms.
Okay, zooming in, we are looking at the atomic grid now.
You see sodium ions, which are positive, and chloride ions, which are negative. They are interspersed throughout the water. But it's not a solid wall of atoms, is it?
No, absolutely not. Think of it like a 3D grid, but the ions do not occupy every single point. There's lots of empty space between them.
And that space is filled with water molecules.
Exactly. And is this grid static? Like a frozen photograph?
I would guess no.
No. And this is the most common misconception. It is chaos down there. The water molecules are rotating billions of times a second. The ions are vibrating, bumping into the water. It is this constant jiggling that ensures the mixing stays uniform.
So when we say a solution is stable, we don't mean it's still.
We mean it is dynamically stable, it is very energetic, but the average distribution does not change.
That leads us to a very serious real-world application. We started with tea, but there's a medical application where this definition is literally a matter of life and death.
You are referring to the saline the fifth drip.
Yes, we have all seen them in hospitals. The clear bag of liquid hanging by the bed, that is usually 0.9% sodium chloride.
It is just salt water, effectively. But the concentration is incredibly specific. And this is where the concept of a solution is non-negotiable.
Why is the homogeneity so critical there? What would happen if it wasn't a true solution?
Imagine if saline were a suspension, where the salt could settle over time.
So the salt sinks to the bottom of the IV bag.
Exactly. Gravity pulls it down. So the patient connected to the drip would get pure water for the first hour.
And that's bad.
Pure water entering the bloodstream causes blood cells to swell and burst. It is very dangerous.
And then at the end?
Then, at the end of the bag, they would get a concentrated sludge of salt that would cause the cells to shrivel up. It could be fatal.
That really puts it in perspective.
Homogeneity ensures that every single milliliter of that fluid, from the first drop to the last, has exactly 0.9% concentration. We rely on the physics of solutions to keep medicine safe.
That is a powerful example. It moves the definition from a textbook requirement to a safety requirement.
Absolutely. It is not just theory.
Now, I want to tackle a counterintuitive example from the notes. It's about stirring.
Ah, yes.
The stirring myth.
So the naive assumption, what I might think if I haven't studied this, is that I have to keep stirring to keep the solution mixed.
Yeah.
Like if I stop stirring, surely the salt will eventually drift down. It's a very natural intuition. We are used to things settling in our daily lives. Dust settles, mud settles.
Right.
But in a true solution, this is false. You can stop stirring, seal the bottle, and walk away. It will stay mixed forever.
Forever, even though gravity is pulling on those heavy salt ions.
Forever. As long as evaporation does not happen, it stays mixed.
How is that possible? Is gravity not working?
Gravity is working, but it's losing a battle. Remember that jiggling we visualized? That is thermal energy, the random motion of the molecules. At the molecular level, that motion is violent and fast. It is much, much stronger than the pull of gravity on those tiny particles.
So the thermal energy essentially overpowers gravity.
Correct. The particles are moving too fast to settle. We call this being thermodynamically stable. The mixture is happy in that state. It does not need your spoon to help it.
That is a key insight. So stirring helps it dissolve faster.
Yes, stirring helps the kinetics, the speed, but it is not required for stability. Stability is thermodynamics.
We are getting deep into the physics now. Let us pull it back for the listeners preparing for their exams. We want to give you the exam-safe clarity lines.
These are the checkpoints. If you are writing an answer about solutions in your board exam, these are the concepts you must verify.
Let us run through them. Checkpoint 1, the scale.
A solution is homogeneous at the molecular level. It is not enough to simply say it looks mixed. You must specify that individual particles are separated by the solvent.
Checkpoint 2, the stability test.
Solute particles in a solution do not settle on standing. If it settles, even a little bit, it is a suspension, not a solution.
Checkpoint 3, appearance.
A solution creates a single phase. It is uniform, no layers, no floating bits. It looks like one single substance.
And finally, the terminology. This one is simple but very important.
The solvent is the major component, the one you have more of. The solute is the minor component.
And a quick tip from the notes. Unless the question says otherwise, what should we assume the solvent is?
Water. In Class 12 chemistry, water is the universal solvent. Always assume the solution is aqueous unless the problem explicitly mentions something else, like alcohol or benzene.
Excellent. We have covered quite a journey today. We started with a morning cup of tea and ended up discussing the molecular dynamics of an IV drip. Let us recap the main takeaways of this deep dive.
What to summarize?
First, the core idea.
A solution is not just a mixture. It's a specific type of homogeneous mixture where the solute is distributed at the molecular level.
Second, the analogy.
Remember the concert crowd. The solute particles are like friends lost in a mosh pit, completely inseparable from the crowd and distributed everywhere.
Third, the real-world application.
Remember the saline, the effete. The reason it is safe is because solutions do not settle. They are thermodynamically stable.
And finally, the clarity checks.
Single phase, no settling, uniform throughout.
Friends, understanding this word homogeneity is not just vocabulary. It is the key to all of Unit 1. In the next deep dives, we are going to calculate concentration, vapor pressure, and boiling points.
And all of those calculations, they rely on the assumption that the mixture is uniform. If you understand this foundation, the math will make sense. You are calculating the properties of a stable, uniform system.
So the next time you stir sugar into your tea, watch it disappear. and realize it is not gone. It is just dancing with the water molecules, suspended in a violent, perfect balance that will last forever.
Or at least until you drink it.
Very true. Thank you for listening to this deep dive into types of solutions. Keep your concepts clear, and we'll catch you in the next one.
Study well.